Good afternoon. Good afternoon. Good afternoon. Oh, thank you. Yes, we are up for another exciting seminar. It's been fun, and I think we're going to continue. We are lucky to have Dr. Bradley Miller to tell us all we wanted to know, or we were afraid to ask about GIS. Dr. Miller grew up in the hills above the Des Moines River, not too far from here. He earned his bachelor's and master's degrees from Iowa State University. After tripling the number of undergraduate students in the agronomy major at Iowa State University through I'm an agronomist for a campaign, he decided it was time to do something different. From his previous research activities, a recurring theme he had heard that available soil mass were not sufficient to meet precision agriculture and modeling needs. With a solid foundation from one of the best soil science programs in the world at Iowa State, Dr. Bradley sought out a scientific discipline that focused on maps and geography. In 2013, he earned a PhD in geography from Michigan State University, and then he spent a few years experimenting with digital soil mapping techniques in northeastern Germany. Today, Dr. Miller is an assistant professor in the Department of Agronomy at ISU, where he teaches introductory Spatial Technologies course in the fall and advanced digital soil course in Alternative Springs. He manages an active research program using GIS to improve soil math from the field to the regional scale. His research activities were recently recognized by the International Union of Soil Sciences with the Daniel Young Scientist Medal hugely reviewed in Brazil. Dr. Miller.
Thank you, Dr. Miller. All right. Well, I do have too many slides because I was trying to attempt to cover everything you want to know about GIS. I probably won't quite accomplish that in the next 40 minutes or so, but I'll take a shot at least scratching the surface. Now, the title of my talk is GIS a Science? And implications for soil science. So the first part is actually kind of a controversial topic out there. Not everyone sees GIS as a science. Some argue that it's just a tool. And there's different ways that we can evaluate that. And quite frankly, I use that as a presentation title to attract more of you, and I don't know where this goes. All right, we'll try that. All right. So I see I pulled a few extra people to the soil science seminar, so hopefully that title did its trick. But there is certainly a question. A lot of you use some kind of geospatial technologies in your research. Either you look at maps, or when you go out in the field and collect a sample, you're logging its location with the GPS. So in some way, geospatial technologies is affecting soil science. And so the question of is GIS a science has interesting implications for how we apply it and use it in soil science. To answer this question, of course, the basic question is, what is science? And I didn't come prepared with a definition because I want you to be thinking about what qualifies as science for you. So let me ask you, what criteria should we look at as far as determining is something a science or not? Yes, Dr. Manu.
Supported by data.
Okay. What else?
Testable hypothesis.
Okay. Other thoughts?
Can determine cause and effect.
Okay. Anything else that should be on the board? I'm just going to add the kind of all of these things are kind of techniques and important concepts for building to the body of knowledge. So I like to think about that. We want a specific method by which we add to what we knew before. So you don't have to agree with all these points. So you may have certain ones of these as a favorite, you may disagree with some of these, but here's some benchmarks that we can be kind of thinking about as I give some examples of what my research lab works on. All right, so first I want to talk about, a little bit about our perspectives, how we approach science in terms of influencers. And I'm going to draw you out a little bit more. Who are big influencers as far as people? Who established the main kind of philosophies, basic principles by which you use in your science today? It can be recent, it can go way back years.
Carl Springle.
Carl Springle? Okay, who was he?
He was a German scientist that introduced the law of the minimum from Liebig.
Okay, great. And so that says something about the fact that you identified him, how that directs your philosophy and your research, right? Is that fair to say? Okay. Any other?
Fisher.
Fisher. What was Fisher all about?
Statistics.
Okay. Well, what about statistics, in particular for soil? I assume, you're into soil, so how does that affect your philosophy when you do your work?
Philosophy, probably more activity in terms of designing experiments so that you can capture what you have to do.
Right, yeah, so one thing I'll hint at here, and I'll try to stay away from too much, is the history of the quantitative revolution. And so imagining Fisher kind of corresponds with that quantitative revolution where we've been doing science for hundreds of years, but somewhere between 1900 and 1950, all the science is basically said to be real science, we have to do things quantitatively, and we need statistical methods by which to quantify what we're doing. So qualitative methods came out of favor. And I think that Fisher probably corresponds pretty largely with that sweep of philosophy across all science disciplines. Any others? Yeah.
He might not be somebody who is very well known among the group, but he's called Phil Jackson. I worked with him when I was at Iowa State, Alabama University. And Dr. Hornbuckle knows him very well. He is the one who was interested in using microwave remote sensing for soil moisture determination. And that's where I got interested in remote sensing.
Okay. So soil science really is pretty broad. We recognize things like soil fertility, soil physics, soil chemistry, and there's some things we have in common. So something like Fisher with statistics, we like to apply that across the board. Soil fertility person might be more aware of Falau than other soil scientists, things like that. So I just want to give a little bit of my background to introduce you to why I'm thinking about these things the way I am, but also a little bit of caveat for us to recognize that we all kind of come from different perspectives as we approach these issues. So Michael Goodchild, Esther designates University of California, Santa Barbara, and he will come up here shortly. But basically, he's considered to be the godfather of geographic information science. And he had a graduate student, Ashton Shortridge. Now, Dr. Manu mentioned that I sought out geography at Michigan State. He wasn't my major professor, but I made a very large point to make sure he was on my committee. I wanted to get that geographic information science perspective as I was doing my work with soil maps. So that gives you just a little bit of hints of my background. But if you're wondering, okay, if we determine that GIS is not a science, have we undermined Dr. Miller's entire credibility as a scientist? I hope not, because I feel like I have a strong heritage in my soil science background. So even if GIS is not a science, I'm okay with soil being a science. But in these names, you'll kind of see a little bit of my bias and how I see the world. So these are geographers. These are geomorphologists, and depending on kind of your background discipline, some of these names may seem more familiar to you than others. I'll say that not all of these are exactly PhD advisors. So for example, Marbut technically was a graduate student of William Morris Davis, considered to be the father of American geography, also very well regarded as a geologist. But basically, Marbut was reading the papers by Schaller, and that's what inspired Curtis Marbut to actually go into soil. And the reason I make a big deal about Curtis Marbut is because he was the head of the Soil Survey Division when the practices and methods that we use today to make the soil maps that we use, you probably know it as Surgo. He developed those. He supervised the development of those methods. All right, so GIS. You're probably familiar with turning the acronym of GIS into Geographic Information Systems. That's usually the most common use. And I have a general definition here. GIS can also stand for Geographic Information Science. Sometimes people refer to it as GI science, just to distinguish it from Geographic Information Systems. And you can see that the definitions here are kind of parallel. I have a table here, so we can kind of compare these a little bit better. The first line, framework for versus discipline that studies. Okay, anybody can kind of declare themselves disciplined, so we'll leave it at that. The next line, data structures and computational technologies, too. We'll come back to it, but clearly that's missing from the definition for GIS systems. Gathering and capturing, those are pretty similar, almost synonyms of each other. Managing versus represent. There is kind of an interesting nuance and difference between that, just managing the data versus representing the data. I'll talk about that a little bit. Analyzing data, there's a parallel that adds process. We have data versus geographic information. Those are probably minor differences. So in my talk today, I'll talk a little bit about representation and some of the special nuances we need to consider about those things. Then I'll move more on to process and analyzing, which actually connects very well to data structures and computation techniques. All right, so a quick word about representation. Now, I'm not going to exactly say this is the science part of GI science, but it's an important piece to keep in mind. So this map that you see on your right, the data is the same for all these following slides. But all I do is I change the attribute I go here from equal interval, which is usually the most common, because it's easier for people to read the legend. The distances between the ranges of those values are the same. A lot of times people will simplify those numbers, make it a little bit easier to follow. I didn't want to manipulate the data that much, but on all of these, the difference between the low end and the high end are always 280 on this. Another way that we can classify the data is by standard deviation. A good statistical works. So basically we're looking at the difference of those values from the mean of that field. Natural breaks is another way we could go. Natural breaks looks for gaps in the values, so kind of natural groupings of the data values. And also quantile tries to get the same number of observations or values in each of the categories. More of a histogram approach. The main thing I want to point out here, as I flip between these different slides, is that the distribution of the map changes. The actual values don't. If I look at this field and I look at the colors, I might say all my yields are great. But if I gave the landowner a map that looks more like this, it might be a little more concerned about their crop yields in different parts of the field. So this was really an exercise in communication. So what I want to say about visualization, I'll make one more note. So this stuff can be studied scientifically. For example, you notice that I always used 6 classes here. Research has been done to find that the ideal number of class breaks to have on a map is 4 to 6. The reason for that is if you have much more than 4, you're not showing very much variation in your map. So you basically have limited information being presented. Upper end of 6 is because the human mind just can't keep track of many more breaks than 6. So basically, if you have a map that you start using more than 6, basically you're stretching the ability for the person to interpret that map. But that's really more of a communication science. So with visualization, so yes, visualization is an important part of communication. Communication can be studied scientifically. We have disciplines about how we write things, advertising, general communication, understandability. And I think the important piece here that I want to leave off of is that don't mistake prettier visualization as an improvement in science. I think we've all done this. A pretty map shows up, and we'll say, wow, that's wonderful. And that's part of why I wanted to add that building knowledge here. So just because someone's made a prettier map doesn't mean we've actually learned anything new. It just looks cool. So I add this illustration here. So that's polished coal. So just because someone went through the work of processing that, it doesn't mean they're diamonds. All right. So moving into the data structures part of that GIS science topic. This isn't something that I actually study as a researcher, but there are researchers that are thinking about different ways which we can store data. When I say these are data models, most people in soil science really have their focus on process models. But there's really other kinds of models, and nothing that I present today is going to be a process model. So models technically are simplifications of the real world. So when you have a process model, you have a simplification of a process that you're using as a tool to make predictions. I'll be making predictions today, but not based on a process model, a different style of model. These data models really are about how we represent the spatial information that we have. So the original soil survey map was drawn as lines on an aerial photograph. In modern GIS terms, we consider that to be a vector format. Basically, there's points and lines and so on. So when the soil survey digitized, they traced those lines and brought that into a shapefile, which is a file format for storing a vector data model. Then we started developing GSurgo, where we turned that vector format into a raster format. So instead of lines being part of the data model, now there's all these pixels, or in GIS we call them cells, and each of those cells have values, and they can have values associated with a map unit, and also have other attributes associated with those map units, such as organic carbon, and we can more easily just display those particular soil properties and do different analyses with them. The piece here that if these are different data structures, you have different advantages and disadvantages, but no new knowledge is generated through this sequence. This is the same information. All right. So I'm going to try to prompt you to think a little more geographically. So I'm going to go through a quick history of soil maps. So the first generation soil maps, a key piece in that geospatial revolution. We heard that recently, but back then there was a geospatial revolution because of this invention here. Now there's a little bit of a hint here. There's a chronometer. What is a chronometer?
Watch.
A watch. So before 1773, no one could make a watch accurate enough for us to calculate latitude. When the ships sailed across the oceans, they could hang on to the same longitude pretty well, but if they wanted to go north and south, they were gambling. They didn't quite know what they were doing, and usually they would look for fixed points that they knew, and they just stayed a steady course, and that really affected how things were navigated. It also made it really hard to make maps. So in 1773, we have our first clock that's actually accurate enough to measure latitude, opens up a whole new world of sailing around the world to Europeans, and basically it takes them about 100 years before they start making maps like this. And all kinds of different things are happening. Now, we mentioned a couple of things. So this is considered to be kind of the birth of modern geography. And the big breakthrough here is that when von Humboldt was traveling around on these exploration ships, he was marking his observations quantitatively for latitude and longitude. So we generally knew by that time that we had these climate zones that changed as you went north and south. But if you look at all the maps before this, usually they were straight across, like you see in the southern hemisphere, and this bend up of that temperate region, as it kind of bends north for Europe, that was really hard to observe until you could actually have some quantitative measurement for how north you are or how south you are. So we started making observations that there was a relationship between climate and the type of vegetation that you would find, and things like that. Now, for a soil scientist, hopefully this is not a soil map, but this idea of relationships between climate and vegetation starts hinting at some development of how we think about different soils around the world, why they occur where they do. So here's a key map. You all may study different areas of soil science, but I think that for most of your textbooks, sometimes in the textbooks it mentions that the beginning of the discipline of soil science was with Dokachai. And that began with his book on the Russian Chernozem, and this is the map that basically spurred him thinking about that. So this is a map of humus, concentrations. The mapping style, you'll notice that he didn't actually do the location work that much himself. He has a base map. So this black and white map there, that was there, and then basically he painted on top of that. So there's a geographic technology that he's relying on to think about the distribution of organic matter in the soil. Something a little bit closer to home, just a year before, very similar approach. Thomas Chamberlain, Wisconsin, made a soil map of the soils of Wisconsin. The black and white in the background is largely a map produced by surveyors, and then he has painted on different colors. This is brown again, but this is not organic matter, this is soil texture. And most of the maps at the time are really focused on soil texture. And another reason for that is at the state level, usually kind of your different geologic regions explain a lot of the major differences between them. Because climate's not changing that much across the state, and you're not at detail level enough to look at differences in topography. I'm going to lump these maps in with that first generation of soil maps. Essentially, this is relying on the same technology, but was done county by county. So the first generation of soil maps that he's had systematically done for the United States look like this. And largely, they are kind of parent material maps. That legend on the right, you can't read it, but each of those are basically soil texture classes. A lot of that work was done with plane tables. So I kind of hinted that maybe some of the soil scientists were disconnected from the geographic technology, but these soil surveyors had a close connection with these plane tables. What they were was basically devices that helped them line up angles. If you ever try to draw a map for a friend, like how to get from your house to somewhere else, you notice the scale wanders all over the place. Some things are really detailed, some things are stretched and scrunched together. It's really hard when you're just drawing by hand to keep the scale constant across your map. And that's what the plane table did, is it helped the soil surveyor keep the scale constant as they made the whole map. All right, second generation soil maps. They weren't possible without the invention of air photography. World War I invention, and basically allowed us to make maps like this. Completely changed how we did maps. Now, is there a question, will there be a third generation of soil maps? Those previous maps we just saw, that's what we're using. So we have all these new geospatial technologies, GPS, GIS, remote sensing imagery. These last two, maybe not exactly geospatial technologies, of course, spatial statistics, sure. Machine learning has applications across the board. And I'm going to argue really has a pretty major influence on the research. The reason I put a question mark, will there be another generation of soil maps, is basically this is what our public officials in the government do our soil maps. Most of the United States already have soil maps. It's 9 million square kilometers of soil maps are done. They were all done with that previous generation of technology. And I've been to classifier meetings when I was doing my PhD. I went to a classifier meeting, we're sitting around drinking some beer, and they asked me, so what are you doing for your PhD? And it's like, well, I'm going to try to improve soil maps. And they took another drink, and they were laughing. And I said, what's so funny? I said, go try something else. We already got it all done. They were serious. So I'm hoping to convince more people that, okay, just because it's been mapped once doesn't mean that there's not room for improvement for a lot of societal benefit. All right, so back to our definitions here. Basically, just kind of some cleanup background. I hope that background has you thinking a little more about soil geography. Now I'm going to focus on computational techniques, which does really relate to kind of processing and analyzing the data. So for what my lab does, the best examples I can think of is kind of this process we go through from thinking about sampling design, organizing, and maybe improving our spatial covariates, making spatial and then evaluating those spatial predictions. So it's actually easier to explain these things if I go backwards, and then we can use these as tools to evaluate the things earlier in the list. So let's start with methods of evaluation. So you all have probably used R-squared, coefficient determination, somewhere in your research. It's a common way to basically measure the proportion of variance explained or the relationship between two variables. So basically you're measuring how well does your model explain the pattern in the data. Another metric that I like to think about a lot in our work is RMSE. And this really summarizes the differences between observed values and model values. Maybe I should back up here. You may not always realize this, but when you fit a line to your regression line, that's a model. And you may use it for different purposes. You may never plan to use that to predict something else somewhere else, but that is a model. You're asking how well does it fit. So RMSE, we use that in parallel with R-squared to ask the question, how accurate are our predictions? And depending on your purpose of your work, one may be more important than the other. Okay, so things you've probably seen before. But now let's move on to spatial predictions. It's very common in science to identify the pattern. It's one of our primary tools in our data is just like identify there's a pattern first and see if we can explain why does that pattern exist. So when we use R-squared or RMSE to measure how we identify the pattern, I like to call that goodness of fit. The reason I want to define that is because we can also do another test on what I like to call model robustness. So cross-validation, a lot of you may have used this, but basically you're using the same data set that you use for training the big model, and then you are reserving, say, maybe 10% of the data for validation, 90% for training, and then you repeat the process, say, 10 times or folds, where you change up what is saved for validation, what's used for training. Every time you do that fold, you get a slightly different model. And that model won't be as good as if you used all the data points you had originally because you're using fewer points. At least that's the trend we tend to see in the data. So this cross-validation is really interesting and useful, but I really argue it's a good test to see how much your model really depended on the particular points you were able to sample. So basically ask the question, if you had a different set of points, how much would your model change? So robustness basically means did I get lucky with the points I selected, or was I unlucky, and so on. Now with spatial prediction, if we're really going to test prediction, we have to go another step further. So I really need an independent validation set. I'm leaving this internal, so I'm talking about, say, I'm in a field, and I had 100 samples I used to train the model. If I really want to test its ability to predict, then maybe I have another 20 points scattered within the same field that were never used in any way for the training of the model. That's where I can actually do a test of prediction. And then if I really want to get crazy, but if you think about it, if I want to make a soil map, pretty much everywhere I go, I need to be making a prediction. We can't dig holes everywhere. So surveying is kind of a misnomer, and that surveying kind of indicates that you've observed where things are. But if we're really going to have a spatial model predict soil maps, there's a lot of locations where without digging a hole, I need to be able to make a prediction about what's going to be there. So the big question, if I have an excellent spatial model, is if I take that model and apply it to a different field, I should be able to make a good prediction there. That's really tough, and basically this gradient of these 4 points get more and more difficult, but this is my ultimate goal. So hopefully before I retire, so I'll retire as soon as I have a nice model that I can train it on a field in Iowa and it works everywhere else. All right, so spatial covariates. In making that model, basically we need some things that we can measure more easily or readily to make predictions about those things that are more difficult to predict, the actual soil properties that are potentially underground. So the spatial covariates, I mentioned they're spatial because basically that needs to have that full coverage. So everywhere that I want to make a prediction, I have to have a value of that covariate. So usually we're talking about remote sensing or digital train analysis, something like that. I'm going to leave remote sensing alone today because there's just so many things to cover with GIS. But I think a lot about how can we improve our spatial covariates to make better spatial prediction. And that really brings me to think about types of scale. So anyone that knows me, if you say the word scale in the room I'm in, I'm clutching the arm of the chair, because scale has so many other meanings, and half the time when people say scale, you can kind of figure out what they mean by context. But there's really a lot of different nuances, and to treat this as a science, you have to pay attention to all these little differences. So first, I've already talked about attribute scale. That's one type of scale. Another type of scale that you're probably familiar with is a cartographic scale. A lot of times people think about a map at 1 to 24,000, 1 to 15,840, so on. That's a cartographic scale, ratio between what's represented on the map and its size in the real world. In GIS, that cartographic scale is almost meaningless because you can zoom in and out. But there are certain legacy rules that go with those cartographic scales. That's not the scale I'm going to talk about here. So in geography, we have this concept of phenomenon scale, maybe easier to think of as a process scale. And this is the area over which geographic structure exists. It seems very kind of philosophical, and that's because it is. So basically, we know that climate operates on a very large process scale. It doesn't change very quickly over short distances, but it does change over longer distances. Contrast that with topography. Elevation tends to change pretty quickly over short distances, as opposed to the long distances. So we apply that up with analysis scale. This is what we can actually measure. So in the field or in a GIS, we can't directly measure process scale, but we can directly measure analysis scale. And that's the area over which geographic data is generalized. So this graph here as kind of an example, you can think of the y-axis here as topography. That might be the easiest way to imagine it, but quite frankly, it can be anything you want it to be. I'm just going to add complexity. So each of these are variations of the original here. I'm just going to add complexity to that pattern. So there's really 3 different levels of complexity to the variation of whatever you want to consider that y-axis to be. Now, if I want to measure that, I can analyze across short distances, or I can analyze across medium distances or longer distances. All right. So let's bring this back home to something a little more tangible. How many of you have measured slope gradient in the field? I'm going to wake you up a little bit, so if you can raise your hand if you're still awake. Okay, a few of you have actually done it in the field. How would you know how far across the landscape to look to measure that right? Basically, you're trained. Someone with experience said, here's a calibrate, this is what works. But you do know, if you measured just like 1 meter in front of you, the answer would be different than if you looked 20 meters or a whole kilometer or 100 kilometers down landscape. The answer would change for the same landscape, same location. So really same deal. Depending on how far across I'm looking across the landscape, my value of slope gradient changes for the same locations. So it's a little bit weird to think about it, but there can be more than one answer for what the slope gradient is for the same location. And really what we've done in the field is we've calibrated ourselves by tacit experience, what actually best corresponds with the patterns we see in soil properties. In analysis, the game's different. We calculate slope gradient usually on a raster data model, which basically has these different cells with different elevation values. And basically to calculate slope gradient, we have to fit a plane through a set of points, and then we use the slope gradient of that plane to be the value of, say, x. And the default we usually go for is a 3x3 cell window. Now, if my grid here is a 3 meter resolution, that means I'm looking across a distance of 9 meters by 9 meters. Now, I understand this is actually an area. Just in GIS, when it comes to these types of things, we tend to talk about just one axis because we're talking about squares. So the resolution here technically for each cell is 9 square meters. We just refer to as a 3 meter resolution. So for analysis scale, I'm going to refer to this 3x3 cell window on a 3 meter resolution as a 9 meter analysis scale. But really, calculation-wise, we're not limited to this. We can easily just increase our window size, and we can consider a 5x5 neighborhood around that x. And basically, we can change the analysis scale anything we want. without changing the resolution of the raster. But we get a different context, a different analysis scale by which to connect. Now, just to illustrate the difference this makes, this is slope gradient calculated at that 9-meter analysis scale. And I'm going to bring this to an animation. Basically what's going to happen is the resolution is going to stay the same. I'm just going to increase that window size. And so you can track down the bottom left here, it says degrees, that's the unit for the slope gradient, the 9 meters, that's the analysis scale. And that number is going to go up, and you'll see how that affects the pattern of slope gradient in this landscape. Catch that? You want to see it again? Not adjust your television set. All of these answers are real. These are just the same elevation data analyzed with different analysis scales. So we compare these two. Basically, certainly using large analysis scale tends to have a smoothing effect on the data. So the max slope gradient, when I have this largest analysis scale, is only 4 degrees. Where I have a really small analysis scale, you actually get some places. The real question here is which one of these actually helps us predict soil properties the best. Now I'm going to show you some relationships between different analysis scales and soil properties. But I want to point out that don't get your hopes up too high, because any time that we try to take a single terrain value or remote sensing value and relate that to soil properties, it's not going to be a single relationship. We know it's a complex system. It's always going to take multiple covariates to make a reasonable prediction. Basically, you want each of individual ones to have as high R-squared value as possible so that they're not always additive, but basically you want them to add up so that you can get a reasonable prediction of pattern. So I'm pointing this out here that, yeah, I know that there's going to be low values, and we don't expect a single covariate to predict. So as an example, we have 200 points. This is from Sky Will's PhD dissertation here at Iowa State. So she has 100 points on the north side of the road. That was on a row crop field. 100 points sampled south of the road on prairie. My experiment here is to relate the digital train analysis with soil properties that Sky had observed. And basically, you can see I'm testing different resolutions. Because certainly in the literature, you'll find a lot of conclusions that the resolution affects the correlation between these things. I'm arguing it's not really the correlation, but the analysis scale. What you can see here is as I increase the window size in a certain column, I'm getting matching analysis scales. I just use different window sizes, and basically when the window size times the resolution match, they have matching analysis scales. So here I have slope gradients with the thickness of the Moloch epipedon. And sure, these R-squareds aren't very big, but we get these interesting little peaks. We may not fully reach that peak, and maybe it's coming back down off the top, but relative elevation seems to have a maximum. Profile curvature looks most promising. So certainly if I want to relate profile curvature with the thickness of the Moloch epipedon, 1,000 meters probably is not as good to include in my model as if I had something right around here on the 100-meter analysis scale. And similarly, if I use profile curvature at that 9-meter analysis scale, I'm right back down to 0. So maybe that's not the best one either. So maybe there's a sweet spot in there. But let's break this down a little bit better. So remember that the experimental design has some points in the agricultural field and some of those points in a prairie area. So this is all points, profile curvature, change analysis scale on the x-axis, and watching how that R-squared changes. One, I guess I should point out, notice that the red, green, and blue lines, they track together. That's because they're all matching analysis scales. So really resolution makes no difference here. But if we split the data between agriculture and prairie, that peak only exists for the agricultural points. That peak's almost completely gone for prairie. I don't know the answer to this, but I really suspect that there's some process happening on the agricultural field corresponding with profile curvature at about 100-meter analysis scale that's not occurring on that prairie. That's my guess as I first see that. So similar thing with relative elevation. Relative elevation can be used as a little bit of a predictor. We'd actually get a peak here almost 0.3538, but doesn't exist for the prairie. Now, the slope gradient's interesting. They actually get a peak show up for the prairie here, right around that 300, 400 analysis scale. I'm not fully processed how to work with this data, but I think the main thing is that if we're using slope gradient in our model, it's better to use one that has at least some R-squared value to it than 0. Now, if the numbers and those graphs and those small R-squared values don't really convince you, let me give you a graphical representation. This is the field in Michigan. These are the Sergo lines. If you look at the light parts and the dark parts of the map, you probably have some indication that there are differences in soil properties that the Sergo map isn't really capturing that well. So there's room for improvement. Now, slope, all right, making a quick jump here, but digital hill slope position is a model that I've worked with and we've tried to make in our lab. And hill slope position should be simple enough. I mean, it's not really quantified, but we know that the shoulder is convex, the foot slope is concave, summit and toe slope should be low slope gradients, but one should be at the top and the other should be at the bottom, and so on. So if I just simply use a standard analysis scale for profile curvature, slope gradient, and relative elevation, I should be able to classify those right out. Easy peasy, right? I'll use your color legend here. Nothing in that pattern really seems to make much sense. The reason I chose 27 meters here for this first slide is there's a long time there that our best elevation data was made at the 30-meter resolution. And generally the assumption was when things didn't work out at 27-meter resolution, well, it's probably just at 2-course resolution. We need better data. So what if we increase the resolution to 10? That was kind of the next generation of USGS National Elevation Data Set. It's really just kind of noisy. It doesn't make much sense. I don't know. But what about LiDAR? Yeah, we'll switch it to LiDAR. Any better? So this is not a quantitative result, but basically, visually, I think you can see this is probably not that helpful in predicting distribution of soil properties. But what I did is I calibrated analysis scale with data from soil scientists from the NRCS, what they were observing for hill slope position in the field, and I calibrated the analysis scale to how they were predicting. Basically, I came up with a model that classifies the field more like this. And that's another day we can talk more about this model. Basically, you can see we're getting something that starts to resemble what we intuitively know from field experience, some distribution. The nice thing, once we have a quantitative model like this, then we can take large areas and apply the model and get something like this. So sure, there's area for improvement, but basically I can apply this very efficiently. It works in other landscapes. So here's Texas, an area that we know have complex hill slopes, and we see an alternation between shoulders and foot slopes, which is exactly what we'd expect to see on a complex hill slope. So this model, even though calibrated in Michigan and Iowa, seems to work just fine in Texas, which is actually kind of a weird question. So that's another one of my research questions is it really that transferable? And the great thing about being able to apply this in large areas, we've done this for the whole state. I should really mention, so I want to give credit. So Meyer bond here is what's mixed in here in addition to hill slope position is a floodplain delineation that Meyer's playing around with. We're separating out a floodplain area versus that area is really influenced by hill slope processes. All right, let's talk briefly about sampling design. I'm going to look at a field here, Sorensen, that you know well. I'm teasing this map a little bit, it's a talk for another day. But basically, our job is to explain variation in soil properties. And basically, this is our attempt at starting to tighten up the differences in parent material for Iowa. So here's Sorensen. It's an experimental field. I'm not sure anybody really knows what all has been done to this poor field. So as far as like how management has affected soil properties, this is like the ultimate challenge for us. Everything we have to work with are really related to natural soil patterns, topography, maybe the remote sensing gives us some indication of how the vegetation is reacting to things, but we don't know what the management history is. So the department asked us to make a digital soil map of this field for research purposes. We densely sampled it and made some models here. I should mention the covariate stack. So like plane curvatures in there. This is one of the models selected by our machine learning. That 51 meters means that's plane curvature at a 51 meter analysis scale. And we're stacking up these different digital train analysis along with remote sensing. So really there's a lot of covariates that are getting thrown into the model to make these predictions. And this is really our goal, well, part of our goal for digital soil mapping. So one, produce more of a continuous soil properties map, but then also to produce a map of our uncertainty. So in this modeling process, we can quantify basically on those observations how confident we are. So this is a goodness of fit statistic. So I used all the points to make this prediction here. We got a goodness fit of 0.96, pretty good. An RMSE, basically we're saying to the landowner, well, we think our prediction's within about 0.27% soil organic matter, roughly about within 2 standard deviations. There's another one where we do cat-eye stage capacity for the same field. Also, it looks pretty good with the goodness of fit. But that's with all the points. So really, to put ourselves to the test, we should use fewer points and do some of that independent validation. So we did one version where we selected just a subset on a grid. We used a density comparable to industry standards. So we see industry using somewhere between 0.6 to 2.5 acre grid spacing. This is a 1.4 acre grid spacing. We also think that we can improve our models and basically sample less by being more smart about where we place our samples. So this is really a stratified random design. These points are still on that same grid, partly for practical reasons, probably just to make use of the data set we had. And the background on that is we're stratifying by that digital hill subposition that I was describing earlier. So the idea is that we're having an equal number of points on the toe slopes, foot slopes, back slopes as they may occur in that field. This isn't really high enough relief to really get much of a back slope, the shoulder, and so all the remaining points that weren't used in either of those previous sampling designs, we're leaving those aside for independent validation. So just to give you a sense of how these things are related to each other, the white points here are the training for the grid-based modeling. In relation to the red points, they'll be the validation. Similarly, this is the stratified sampling with those same validations. Just to compare with the industry standard, usually a single point is taken, and I'm saying that rule kind of generally because, of course, what they actually usually do is they come to a certain location and they're taking multiple samples kind of in that area and aggregating it together. That's really bad for us for modeling because no longer we're dealing with points, but basically a representation of an area. But basically, the idea is that they think they have a representative value, and then they make these squares, and they say a single value for each of those squares. And for where we're at with precision agriculture, this may make sense because there's only so much precision you can do with variable rate technology at the moment. But just as a standard here, we run these squares against those validation points. Basically, this map is explaining about 30% of the variation with an RMSE right around 1.37. Now we do the more continuous map with a grid-based spatial model. We get a map like this. Training looks pretty good, so that's goodness of fit. And then independent validation, we expect that to go down, but it's interesting to think about that when we look at different presentations of soil science where the only R squared presented is the training. You know, does it apply anywhere else beyond the data that you actually measured? And because I'm in the business of spatial prediction, I have to look beyond that. And of course, it's more difficult to make predictions. We created the same thing with the stratified based spatial model. We've got a map like this. What's really curious for us, and what we've been thinking about a lot, is that our metrics for describing how well predictions are pretty similar. So we'll go back and forth here. So the validation, the R squared is 0.61 on a stratified based. This 0.58 for the grid-based. Really seems pretty comparable. But look at the map. This is one representation of our predictions for organic matter in this field. Here's the other. Which one's better? So this is something we're struggling with and trying to think through. Certainly we have some people publish in this manner all the time, But this is an important question that I think we need to get to as far as determining what model is the best. Just real quickly, did the same thing with cation exchange capacity. You can see the map by the grid-based, map by the stratified-based, really pretty comparable metrics. The grid-based spatial model actually came out a little bit better on the validation statistics. Kind of similar pattern described there. So I'll just briefly mention that in this small case, we found that the stratified sampling design didn't really enhance our modeling ability that much. We have other work in progress, and I wish Jonas Klidin was here. He has class during this time, but he really helped a lot with this presentation. And some of his work is going a long ways for what we think that basically, if we're just covering a small area, there's not that much variation that the grid sampling basically gets it. But if we're working in larger fields, then that stratified really comes on stronger and helps us build a stronger model. All right, so I'm really running short on time, so I'm not going to talk too much about transferability, but this is kind of, as I said, kind of the holy grail. And this is some of the work I did in Germany. I'm going to flip through these kind of fast. If you want to stay around longer, I'm happy to go back and talk about them more. But we have, I just want to show you some final results on that. So you can see we have several different sampling campaigns. I can compare them in different ways. So usually when people talk to me about digital soil mapping, the first thing they start talking about is kriging. Kriging is great when you want to model within a field relatively short distances between points and relatively dense sampling points. It really relies on the concept of spatial autocorrelation. And for soil properties, your spatial autocorrelation range is somewhere between 5 and 200 meters, depending on the soil property, kind of rough ballpark. So if you make predictions, one, more than 200 meters away from the point you sampled, probably not kriging. Another example is kriging is working in the geographic space. That means that you can't make predictions outside of the field or the area which the sample points were taken. This MLR, multilinear regression, is largely that machine learning that we're talking about. And the hope is there, because we're not working in the geographic space, we're working in the feature space, which means the relationships between the soil properties and features, attributes, those covariates. So I'll point out here that so these are modeled there, and you have some details. But basically, the MLR is somewhat competitive within the same field. Just outside the field, everything breaks down, but this particular one that used leaf area index calculation off the QuickBird satellite actually held its own a little bit. And then there's a larger, greater field beyond that small field that all this work was being done. And you can see that both of the regression models start to recover a little bit as far as R squared. So, yeah, nothing to write home to mom about, but there's some promise there. Now we do it the other way. So that big field, we have stratified points and just 28 points stratified. I could Krieg on those points, but then the points are much further spaced apart, and my R squared value, as I test against these independent validation points, now it's there, but it's much weaker than that 0.7. But then just those, so and then these R squared values here are actually holding pretty steady and pretty well. But it depended on what we provided the model for as covariates. So this model here for covariates relied entirely on digital train analysis, did not do all that well. But when I was able to use that remote sensing information, it actually came out all right. And that really gives me a lot of hope because, like I said, these are pretty spaced out, just a few points. In general, we want to be building models off of much more than 28 points. But these are completely independent validation points from completely different sets. All right. So I'll leave it up to you to decide if GIS is a science. Clearly, I'm using geospatial technology tools in my work. My only argument that I'll make to try to influence you is that technology is a tool. We all recognize technology as a tool. But the question is, do you need science to make that technology? So So you use that cell phone. You can use it as a tool. It helps you do what you want to do. But how do you improve that cell phone to do more things? I kind of suspect that there's some science back there. Some knowledge had to be gained to make that work well. So with that, I will end not too much after the 4 o'clock hour. And if you really have other questions about things I went through too fast, I'm happy to go back to them. But I should open up. Meyer and Joshua are nodding at this. They're the field reconnaissance for this. This is the Highway 30 road cut towards Tama.
Yep.
Nice little Paley all showing up there. We haven't had too many looks like that since William Walker were jumping around the state. Yes, Dr. Gordon.
What's the root of the terminology slope gradient?
Yeah. So when I started at Michigan State, I was always referring to things as slope. And basically, my major advisor kept adding gradient after slope, and I didn't question it.
In mathematics, we use gradient dy dx.
Right.
Something like that. And it's more of a derivative and differential.
Which,
So it's like a point. Like the way you're describing it here, it's more like you assume a linear slope gradient. Everything is linear, and it's associated with distance. It's like mathematical from calculus, you would have it at the point. The word gradient.
right. Yeah, I'll have to give that some more thought. But yeah, but I think that's another point. As we're doing science, we should be clear about what we're talking about. And sometimes we throw words around a little bit too loosely.
What is a derivative of the change in elevation? It's the change in x over the change in y. It is a gradient.
Yeah, but it's a little bit different than the calculus application. So they're close. But I think there's a subtle difference. So yeah, it is change in y and over change in x. The actual calculation in the grid, yeah, it's a linear. That's how we're calculating it.
Linear model.
Right.
So it's a single slope.
Right.
dy dx can be changing with position. The gradient is, what is it at this point? It be different than the next one. It doesn't have to be linear.
Right. I think what Meyer's going after is as we think about a line, the slope gradient. So basically, the parallels here is, so elevation is original graph. Your slope, I'll just say slope, is your first derivative. And your curvature is your second derivative. So there's some parallels, but not quite the same as in calculus. You're right. I see what you're saying. Yeah. Yeah.
Could you go back to the slide that had the R-squared values for models?
Sure.
And then what was MLR again?
Sure. Multiple linear regression.
Okay.
And really, that's shorthand. What was actually used here was QBIST machine learning, which develops a rule-based machine learning multiple linear regression. So it divides the data up into different categories by rules, and then there's a separate multiple linear regression equation on each of those categories.
Your research platform, or what would you start to think of?
That, yeah, man, I think that's one. It's a really big challenge. Other is that's also the impetus to update our soil maps, because all that's been happening. When the average soil map in Iowa is 30 years old, it's a good chance that management, which is designed to change the soil properties, has had its impact. Our thoughts on it is, one, recognize it's a huge challenge, because we're not going to get the management records for all the fields in Iowa. But we can think about using field boundaries as a predictive covariate. So it's not necessarily knowing what they did, but knowing that each field has undergone slightly different management, and to make it grouped together. So that's a possibility. The other hope is that the vegetation is reacting to the soil properties as they are. So when we're using remote sensing that is using, say, a metric like NDVI or something like that, that might, and if we can tease out the effect of natural topography, so certainly areas that are a little more wet, a little bit more dry, they're going to have crop differences based on that. So if we can tease out that part of the variation, maybe what the remote sensing brings in is what the differences in management have caused. So, and that's kind of an interesting thing. So of course, my own graduate student determines cause and effect. When we're in the business of spatial prediction, and there's some really fantastic philosophical papers out there. Sometimes our goal is prediction, and sometimes our goal is cause and effect. And sometimes just getting a good prediction is a good goal. So a lot of times for our spatial prediction models, I do hope that when we see a covariate pop up that says, oh, we didn't think this was related to any soil forming processes that we knew about, hopefully that prompts us to go out in the field and investigate. But at the same time, just because it's useful may actually be useful. So when I talk about the vegetation, we can tie it to processes that we know about the soil landscape and make some guesses for why those patterns exist. But we may not always be able to make that full connection and say, okay, this pattern here was caused because farmer X was using this tillage practice. That'd be kind of next here.
But some properties are dynamic and others can be stable. Can you use the stable one like texture as the predictor and make these other than using, say, organic carbon?
Yeah, I think that's a really good strategy. I think there's a reason that the soil survey tends to only report the more static soil properties. And largely my focus at the moment is those static soil properties because just improving the existing soil survey map would be a huge progress. But of course, the big interest in the, certainly in this state, is those dynamic soil properties. We're talking about nutrient management, as far as precision agriculture, as far as water quality, all those things is more about the dynamic soil properties. So we're playing around with the dynamic soil properties a little bit, recognizing that there are even harder to predict than, say, soil organic matter, soil texture. But yeah, so we're doing both at the same time, but I really think that once we lock down the static soil properties, then getting those dynamic soil properties, there'll be less variability to deal with. They'll still be difficult, but at least we can maybe control for differences in texture and on the hydrology and things like that.
Any more questions for Mr. Miller? Well, then let's